Registers and memories are the topics of this lesson. They are incredibly important. The way things are organized dictates their performance. It also affects energy consumption and parallelism. Data has to be fetched from memory, stored in registers, manipulated in function units, and finally put back into registers or memory. Organization of registers and memory affects both performance and energy as the data gets manipulated and is transformed. Registers are one of the most important entities in any microarchitecture, no matter what. And this is especially so since the advent of RISC, which mandates all the data to be in registers before we can do anything with the data. In VLIW, the same philosophy is carried. The data has to be in registers. And due to a lot of parallelism, in VLIW we have lots of registers and they had to be put in terms of different clusters. So what are registers? We all know that registers contain data, and registers are individually named as R0, R1, R2, unlike memory, which just has an address. Since we have lots and lots of registers, sometimes the registers are organized into files or groups. So let's turn our attention to how registers are organized as far as the superscalars or VLIW is concerned. We have a multi-ported register file because of large number of registers. Why so many different number of ports? Obviously to facilitate the data movement in parallel. At least 2 operands have to be read in parallel per operation, and there are multiple number of operations that are concurrently executed. That's why such a large multi-ported register file. These registers are connected to the function units, multiple one of them which execute in parallel, and then the results are fed back to the register file, and they also have a bus to go towards the memory. In VLIWs, there is no bypassing involved, in which the registers and register files are directly connected to the function units via the data paths. On the other hand, in many other architectures, the bypassing is a must. Bypassing is also called as forwarding, which means the results are automatically forwarded to the next instruction, which takes it as the input operand. In VLIW, however, there is no bypassing involved. Those results are copied separately via another network into the destination registers. In other words, there are no implicit register writes unlike the other architectures. You may ask the question, why is it so? Why is there no forwarding? Why there is no implicit register write? The VLIW register organization is quite complex, and the destination of where that operand should be can be different from where the source is. In other words, there are separate instructions to move the operand from one register to the other, giving more control and flexibility to the programmer. Having seen the basic organization of registers in VLIW, now let's look at the important aspect of clustering. There is a lot of pressure on register files in VLIWs, especially there are a large number of operations which execute in parallel, and all that data has to be fetched in parallel and written in parallel. And in order to facilitate this large bandwidth, the registers, the function units are all clustered and are split as against one giant register file and a large number of function units attached to it. So here is an organization in which we have the register file split into multiple different parts, and to each register file part we have some function units that are attached. There is a interconnection network which connects these register files to one another, and these clusters are therefore connected through this interconnection network. You can see that assuming 8 execution units with each with 2 input and 1 output, at the peak we'll have 16 reads and 8 writes to the register file, and therefore we need to cluster them into these different parts as shown over here. The traditional solution involves a large multi-ported register file. In other words, we have just single file and we have lots and lots of ports here to facilitate the data movement. However, what is the catch here? The problem is scalability. This design does not scale for VLIWs because the need is for very large number of parallel data movements in terms of both reads as well as writes. In other words, as the data requirements grow, the number of ports grow. The area of the register file therefore grows square as to the number of ports. The latency slows linearly, and the bypass network that is needed becomes very complex. in fact quadratically complex as the number of ports grow. The problem about the area really leads to the clustering solution, and the solution involves breaking down a monolithic register file into smaller units. Separate units can be accessed locally for the register files. And in order to facilitate the communication across the different clusters, we have different intercluster mechanisms, some interconnection kind networks. And then finally, to go to the memory, we do have a memory interface unit. Most of the communication here, as you can see, will be local within a cluster. There will be a little bit of communication between different clusters, and then there will be much lesser communications going to the memory. In this way, we are able to provide scalability here by replicating these units as many times as we want. Of course, single monolithic register file is an ideal solution in terms of latency, but in terms of the parallelism, those designs don't scale, so this is a necessary evil that we have to live with. Having seen the motivation for clustering, we are now going to take a look at two different kinds of clustering. One of them is architecturally visible or is exposed at the ISA level, and the other one is invisible and it is hidden from the ISA level. Let us look at the architecturally invisible clustering solution. In this, the file appears as one large register file to the compiler, and the compiler has to make these decisions in terms of the register allocation. So how are the registers managed, and how is the operand from destination to source moved? Who does that? In this situation, because the compiler has no knowledge about this, the hardware is the one which copies the registers from one to the other. Remember, in VLIWs, we do not have any bypass network which automatically allows this copying. So something needs to happen here to detect the destination and to detect the source operands and to make sure that those registers are copied from the source to the destination. And due to this reason, detecting when copies are needed and how to carry out those copies from where to where is a hard problem. Such detection has to happen across multiple pairs, and therefore the solution is not scalable. Another implication of this design is that all the registers need to be exposed in one operand field. For example, if you have 1024 registers, you will need a very large operand field because you will have to access each one of them. Another problem is that the copying occurs depending on the source and destination registers, and there are latencies involved in this, and because of this, the destination instructions are stalled, and such stalls are invisible to compiler. So all this is against the VLIW principles of exposing the implementation to the compiler and let it be in control. Against such VLIW principles, however, a superscalar DEX Alpha 21264 processor did implement this strategy and was not too much successful there. Let's now take a look at the more popular and more practical clustering mechanism, which is called as visible clustering. In visible clustering, ISA must include a way to specify operations being assigned to a cluster. And then we have a choice of carrying out whether a copy between the clusters in an implicit manner or in a more explicit manner, which is controlled by the compiler. In either of those mechanisms, a register or a group of registers could be copies from one cluster to another. In implicit copy mechanisms, the operations may do the reads and write of the operands in non-local registers transparently, and so the code generation is quite simple without knowing where the operand resides. However, the drawback of implicit copy is it is complicated for scheduling and scalability issues. In other words, if you have to get a non-local operand, it costs latency again, and that will slow down and throw the pipeline out of balance. In case of explicit copy, one can only access a remote register through a special operation, and that special operation is under the compiler's control and has to be inserted at the right place in the code. Such an explicit control allows a great scheduling and scalability, and there are no surprises involved there. However, this may lead to an increase in the pressure of the register and also the code size, because many times it might be better to fetch and replicate the register at a local cluster, and that means 2 or more copies could reside of an operand and therefore could result in a lot more register pressure. We have seen the pros and cons of implicit and explicit copies in terms of compiler and scheduling issues. Now let's take a look at the underlying hardware solution issues. In terms of performance, both implicit and explicit copy operations increase critical path and increase latency as well. Some results show that dividing a single monolithic file into 2 clusters costs 15 to 20% extra cycles. In terms of dividing it into 4 clusters, incur 25 to 30% extra cycles. Why these extra cycles? Because now one has to generate all these instructions which will fetch remote data from remote registers either explicitly, or we'll have to do the implicit copies, which will again cost task cycles. As we have seen here, partitioning a register file into clusters also increases the critical path and slows down the clock. Therefore, we have to offset it. So in other words, we'll have to increase the clock to 15 to 20% the original value and put a bypass logic so that the clustered configuration comes back to its original performance level in terms of an equivalent non-clustered configuration. Now such increases in the clock frequency are pretty modest, and therefore this design is a practical design choice for VLIWs. So we have seen some foundational principles of clustering, their effect on copying, the compiler issues, scheduling issues, and the hardware design issues. Now let's test our knowledge of clustering through a simple quiz. Please mark all the statements which are true here with a check mark. The first sentence says that the partial interconnect clusters promise better scalability. The second sentence says that the partition register files have lower access time but occupy a larger area and dissipate more power. And then the third sentence says that the bypass network of a clustered VLIW is also partitioned. Please go ahead and mark those choices now. The first statement, partial interconnect clusters promise better scalability. This statement is true. The reason is we do not need a complete interconnectivity between the different register files because the types of communication that can occur between the register files or between the partitions of the register file is quite sparse. So a partial interconnect is quite sufficient, and in fact, if you have to implement a full interconnect, it will cost a lot of die area and it will not work, especially when you have a large number of clusters. Therefore, partial interconnects provide better scalability. The second statement is that the partitioned register files have lower access time but occupy a larger area and dissipate more power. This statement is false. The partitioned register files have, in fact, a better area requirement and dissipate less power because they have less number of ports and so on. The length of the data path from a register file to a function unit in partition register files is also smaller, and therefore they have better latency or lower access time in fact. How about the last sentence? The bypass network of a clustered VLIW is also partitioned, and that statement is also true. Due to a large number of registers that participate in the bypass network, it must be partitioned, otherwise it will not scale. Not only it is partitioned, but it is also made hierarchical. Many times we have heterogeneous register files, which means the clusters are dissimilar. Typically, the partitioning is done sometimes by the data types. In other words, we have separate clusters for integers and the separate ones for floating point registers. Similarly, we have what are called as predicate register banks. In other words, the contents of those registers do not commit until the predicates become true. This is especially true in speculated computation, such that we go ahead and generate the results in those registers and have attached predicates to them. When the results of the branch conditions are known, those predicates are turned on or off, as in the predicated execution, and then those registers banks get activated in terms of their reads or writes. Similarly, we have branch register banks which decide which side of the bank and the instructions in them are to be executed. The use of predication and speculation especially allows us to become very aggressive in terms of following the execution. Otherwise, the compiler optimizations may become too conservative because a lot of information is unknown statically. In such cases, through the use of predication, the data flow of the program is simply executed as though it were executing in a predicated register file, and turning on and off those files implements the right data flow. Let us continue the discussion about the registers. Apart from the registers for integers and floating points, there is another classification of registers depending on their intended use. The registers that hold address are called as address registers. The registers that hold data are called as data registers. In VLIW, however, the register files are general purpose. And in fact, the compilers allocate registers regardless of their intended use. So in other words, they do not distinguish whether a register holds a data or whether they hold an address. However, that is not the case in DSPs. In other words, the DSP architectures distinguish between address and data. In fact, DSPs have separate registers called as address registers. What do the address registers do? They hold the memory addresses so that one can go there and get the data. These are typically long integers, and in fact, the address registers could also be interchangeably used for holding long integers as data. In addition, of course, there are regular data registers for holding the data. These data registers could hold different varieties of data, especially in DSPs, which could differ in terms of their operand widths. They could hold 40-bit data, they could hold 21-bit data, they could hold as small as 7-bit data, and the purpose is to distinguish between different data types for specific operations. You may ask why there are different operand width registers. Remember that DSPs are ASICs, or they are special purpose processors, and they are intended for extremely high bandwidth processing for certain domains. Now, different data types and their widths are specific to domains such as signal processing, and therefore DSPs have special registers for those. Because registers could be interchangeably used, in DSPs another interesting thing is certain registers are connected only to certain function units, such as accumulate register, for example, is connected only to an adder. Now, if the operands are not carefully kept in the right registers, we may have to pay a penalty of moving those around so that they get in the right registers before one can do certain operations on them. If this is not done carefully, we might carry out certain redundant register movements, and therefore the DSP compilation is quite complex, trying to make sure that the right operands are in the right register at the right time, and in case there is no room for them, then try to minimize the register movements. Having talked about the data and address registers, now let us look at certain special features of the register files. Now remember, the difference between a small set of registers, such as 32 or maximum 64, versus 1024 registers is that the large set of registers are organized in terms of a register file as shown over here. Now the register files is a whole big bunch of registers. The question is, how do we access a specific register in that file? What we have is two different ways of accessing specific registers in the file. One is using indexing, trying to go to a specific register by using an index. And the second way of doing it is called as rotating register files. In rotating register files, we keep growing the access to the files in this particular way, and then finally when we run out of the registers, the next register that is to be used is we kind of go back and start all over from the first register. So that is why it is called as rotating register file, which rotates as per the access of the registers. Let's discuss now index registers files in terms of how they look and how they work. What we have is again a large set of registers organized into a big file, and the way it works is we have a base, which is where the registers start, and then we have an offset to a specific register where it can be found. So in general it looks like this. Here is where the register file starts, called as the base. That is where the 0th register is found. And then there is something called as offset, which is added to the base where the ith register is found. This is, for example, the ith register. In some cases, the compiler manages the register files as a cache of machine stack. In other words, a part of the machine stack where the local variables of the function are held are allocated through such a register file, and the compiler manages that as a cache. And how does the access work in such cases? This is your base, and in addition you have an offset which looks like this. In this particular way, a particular register is accessed on the frame by using a base and an offset. Let us look at an example of a function call that is held by the index register file approach. Here is an example of a frame that is allocated using a register file. What is a frame? A frame is an area of memory where the input, the output, and local variables of a function call reside. In addition, in a frame, you always have a return address where the function call will return. So compiler can explicitly allocate a variable section of the register file for processing the frame as shown over here. This frame, as I mentioned earlier, is used for procedure call and return for stack management. And as you can see here, you have input parameters, locals, and outputs. And what is the advantage of allocating the frame in a register file? The biggest advantage is it eliminates the register spills and restores at call boundaries. Imagine a set of registers being given to one function. When the function calls another function, so what happens to all those variables which are in those registers when a given function calls another function? All those variables will have to be stored back into the memory, and that is called as a register spill. After the called function returns, all those values have to be restored and put back from memory into those registers, and that is called as restore. Now remember, this has a tremendous amount of overhead at the call boundaries. If you are careful in allocating this frame in different part of register file than in another part, you can avoid this overhead because this set of registers do not interfere with the other ones. And so the caller can have a given set of registers here, and the callee can have another set of registers over here. And by doing this, one can eliminate the register spills and restores at call boundaries, which can save a tremendous amount of overhead. This is easily accomplished through the index register files approach as shown over here. The second type of special register file is called as rotating register file. What is a rotating register file? It is a different kind of an index register file for which the base of the file periodically cycles across the registers. For example, consider this register file. At the beginning, it is completely empty. In other words, no registers are allocated out of it. So initially the base is over here. This is register 0, and the registers are given out in this particular way in an increasing index manner. And so the number of available registers become lesser and lesser. And in this particular manner, this is the last register that will be given out. Now remember, what is going on concurrently is the registers are also being freed. So let us say that some registers which were given out earlier, they have become freed here because all those calls which happened have completely done. If we take a snapshot of this process, here is how it looks. These are the free registers, and these are the ones which are occupied. Now under certain situation like this, the base shifts from here to over here. And the new registers which are given out are given out from the beginning, which is over here. And in this particular way, the set of registers that are being given out are constantly rotating, going in this particular way, and then once this is full, going back all the way and starting all over again. And so it gives us an illusion that the base is moving towards the right. Initially the base is over here. Once something is freed, the base moves over here, then something else is freed, and so on. And finally, when things get filled up here, this becomes the base. You add an index to it, and you take a modulo to get a register over here, and this is the next free register which is given out from here, and that's why this is called as a rotating register file. So as you can see, by shifting the base, we are changing which register gets allocated because we are allocating them in sort of a wrapped manner. And so rotation is a form of dynamic register renaming in which when we wrap to the beginning of the register file, we start reallocating from there. And so rotation is very useful for what is called as software pipelining, in which as the iterations execute, the registers are given out in a cyclical manner for the next few iterations. As we'll see later, the compiler can generate a very compact code to carry this process out by using rotating register files. And this feature was implemented in Itanium as a dynamic rotating register files. What about the latency of special register files as against individual registers? The moment we have a large number of registers, we have to implement either indexing or some other way to access them. And all these have costs. For example, if we implement the access to a large register file as base plus offset, then the calculation of base plus offset sits in the critical path, can slow down the access, and can result in higher latencies. It's time for a quiz now on the registers and our knowledge of how these register files work. So what we have is different sentences given to you, which I'm going to read, and you are going to fill in the blanks over there with the right answers. The first sentence is, VLIW instructions are separated into primitive instructions by the blank. Fill that blank in. Second sentence is, during each instruction cycle, one VLIW word is fetched from the blank and is decoded. Fill in that particular blank. The third sentence is, instructions are then issued to blank to be executed in parallel. Fill in that blank. And finally, since the primitive instructions are from the same VLIW word, they are guaranteed to be blank. So for all these blanks that I have mentioned when I read these sentences, you have to identify what is the correct word that should be filled in. So please go ahead and write your responses now. Let us take a look at the answer for the first sentence. VLIW instructions are separated into primitive instructions by the compiler. Remember the grouping of instructions, the primitive operations into a large VLIW instruction. Who does that? The compiler is the one which does it. Let's take a look at the second sentence. During each instruction cycle, one VLIW word is fetched from the cache and is decoded. To be more specific, what kind of cache? This is, of course, the instruction cache. Remember that these large instructions, VLIW instructions, are fetched. They're separated into individual sub-instructions, and that happens as a decode operation. These large instructions are, of course, resident in the cache. Let's now take a look at the third sentence. Instructions are then issued to the function units to be executed in parallel. Remember, after decode, what happens? Goes into execute stage. What is the execute stage here for VLIW? Each one of those individual instructions is then given to the respective function unit to be executed. And they are all independent, so they execute in parallel. Now let's take a look at the last one. Since the primitive instructions are from the same VLIW word, they are guaranteed to be independent because the compiler has made sure that they do not have any dependencies, and that's how they got grouped into the same word, and therefore they are guaranteed to be independent. Now let us test our knowledge through a quiz. What I have are the different addressing modes which are written over here, and on the right hand side I have the meaning of each one of those. What do they exactly mean and how they are implemented? So we have boxes in front of each one of these addressing modes, and you are supposed to pick up the right letter from the right hand side and fill it in. The first one, register addressing. The second one, immediate addressing. The third one, register indirect addressing. The fourth one, memory indirect addressing. The fifth one, indexed addressing. And then the last one, offset addressing. Now let's take a look at what these instruction modes mean in terms of their implementation and what do they do. Alternative A, it says a constant coming from the instruction word. Alternative B, it says an absolute register address in the instructions. Alternative C says use the register for holding an address. Alternative D says use a memory location to store address for the operation. Alternative E says two separate variables in the register so that we have a base address and we also have an index to a register to hold to. And then finally, F alternative says hold the base address and we have an offset from that base address. Please match these different alternatives with the addressing modes that I mentioned earlier. In the boxes next to the addressing modes, please write your responses. Go ahead and write your answers now. So register addressing, what does it really mean? The correct answer is B. The alternative B says an absolute register address in the instruction. Such as if you say R3 or R5, that is register addressing mode. And what it means is we are actually giving the number of that register and putting that straight inside the instruction. The second alternative is what is immediate addressing? And the right response is A. Immediate addressing means the constant coming from the instruction word, and that is really directly embedded into the instruction itself, such as ADI R5, 7. That 7 is an immediate operand which is directly embedded into the instruction. The third addressing mode is register indirect addressing. The right answer is C. It says use the register for holding an address. In other words, you are going to the memory not directly by not putting the address directly into the instruction. However, by putting it into a register you're accessing that part of memory through the register, and that's why it is called as register indirect addressing. Now you may ask me, why is this mode used? Because the memory addresses can be very long, and we may not have enough number of bits to hold them as a part of the immediate addressing. That is why we will try to use register indirect addressing to hold those addresses. Memory indirect addressing. This is similar to register indirect addressing, and the right answer is D here. The only difference is we'll use a memory location to store the address for that operation. In other words, we are going to the memory location, getting the address, and then using that address to store or read a value into that location. This is very similar to a pointer dereference and is typically implemented as a memory indirect addressing mode, wherein the pointer is giving us the location of the memory where the address of that operand resides. The next mode is index addressing, and the right answer here is E. E says that we have two separate variables in registers. So we have the base address and we have an index of a register to go to. And finally we have offset addressing, and the correct answer here is F. What we have here is we hold the base address and we have an offset from that base address inside an instruction. So what is the difference between indexed addressing and offset addressing? In index addressing, we have an index to a register, and that in turn holds the address. Whereas in offset addressing, the offset itself is a part of instruction and it's cooked into the instruction. So when we have a very large offset which we cannot build it into an instruction, we'll have to use an index mode in which we'll put that big address into a register and we'll use that index of that register to go to that particular address. Hope this addressing modes and their matching with their different intended uses and how they work gives you a very clear picture of the addressing modes. Let us briefly talk about the memory architecture for VLIW. As we have seen, VLIW is a load store architecture and mostly reuses the RISC memory addressing concepts. What is a RISC concept? RISC concept is to separate the loads and stores as separate operations from other arithmetic operations. That way, the memory instructions flow separately and the other arithmetic logic instructions flow separately and can be kept simple. The exact same concept is followed in VLIW, that is, the load stores are separate and the operands must be in registers before one can do any other operations on them, just like the RISC processing. But one of the differences is that there are special addressing modes which are supported in VLIW, and the main reason is that the number of registers supported in VLIW is very large. So we have indexed addressing mode and so on. We do have separate registers for data and address, and the main idea here is to give more flexibility and control over the data layouts to the compiler designer. And by creating address registers, the compiler designer can arrange these data layouts in certain ways. In fact, later in the class, we are going to see an interesting optimization which is facilitated because of the address registers. To keep the bandwidth high, in VLIWs, the memory is typically banked, and the banking of the memory also makes it energy efficient. What is banking? Banking means the big block of a memory is separated into different units which are called as memory banks, and that way each of the banks can supply an operand supporting concurrent reads and concurrent writes across the different banks. If it were to be one big block of memory, then they will get sequentialized, and the banking helps us to parallelize the load stores. In fact, not only the memory is banked, but is typically arranged in a way that the two operands that are needed for an instruction could be concurrently fetched. So if this is the organization that is followed, that architecture is then called as XY memory. In other words, one bank provides the first operand, which is called as the X bank, and the second bank, which is called as the Y bank, provides the second operand, and therefore an instruction can execute much faster, getting both the operands in parallel from two different banks. The memory organization could be even more complex in some very special embedded systems. GPUs, which many of you have heard about, graphical processing units, are nothing but special embedded systems. They were used mainly for graphics processing, such as image processing, multimedia processing, and so on, GPUs became very popular as the biggest gaming chips, in fact. But now, GPUs are finding uses everywhere, not only just in gaming or multimedia. They are being used as a part of SoC or system on a chip very frequently. So how are the GPUs different? Here is an example of typical memory that are supported by the GPUs. GPUs has what is called as a constant memory. What does that mean? That means all the variables which do not change throughout the lifetime of the program could be put there, and these behave as constants. The second piece of memory is called as shader memory. What is a shader memory? Remember, in a pixel, we could have different bits which represent different attributes. One bit could represent, for example, luminosity. Second bit could represent the color. Third bit could represent texture, and so on. And whenever a pixel is to be processed, this group of values has to be brought in together. So the same concept is extended here as what is called as the shader memory concept, in which a group of related values which are to be processed together are held together and organized together in that memory so that the access to them is very, very fast. And so shader memory very efficiently supports a group access. And then we have two other kinds of memories here, shared memory and a local memory. So each thread in the GPU executes in parallel with many other threads, and each thread's accesses have to be supported very, very fast. And if they are coming out of a local area which is local only to that thread, that memory is called as the local memory. In addition, for threads to communicate and get values which could not fit into the local areas, we also have a shared memory. You can see that GPUs are highly parallel, or rather data parallel processors, and in order to support such amount of very high parallelism, now let us see the effect of addressing modes, especially on the execution of the instructions. Here is a typical pipeline that we had looked at earlier, in which the instructions are fetched, they are decoded here, then they go into the execute stage. During this stage is where we decide to find out where the operands reside and fetch them, and then carry out the execution in the ALU. Then we have a memory access for load store type of instructions, and then we have a write back in which the results are all committed. As you can see here, the address calculation happens in this critical stage, which is execute stage. And the other stages are independent of the addressing modes, but this is the stage which really depends on it. For example, if we do index addressing mode, we got to go to the register, get the address from there, add it to the base register, and then finally go to the memory and get the operand. All this has to happen. And so the more complex the addressing mode is, the more complex processing takes place here, which has a latency associated with it. This is on the critical path, and therefore the addressing modes play an important role in the amount of latency or throughput that is achieved. Keeping the addressing mode simple causes the latencies to shrink, but then it causes more instructions to be generated to get the data from the memory, and gives less freedom to the compiler to organize the data for efficiency. So there is an inherent trade-off here between the complexity of the addressing mode versus the freedom given to the compiler for the data layout and for causing much larger efficiencies overall in the execution. Although many different modes are supported, in embedded world, many accesses still get mapped to the base plus offset type of processing. For example, when we want to access an array element, the base of the array is the starting point of the 0th element of the array, and the index is used for generating the offset, and the two are added to access a particular array element. Similarly, for structures, by laying it out in the memory, the compiler generates the offsets and adds those to the starting point where the structure resides in the memory, using that as the base address. Base plus offset is a very important mode that is useful for embedded systems. Here is why. If we did not have this mode, then we will have to have a special instruction for adding those two, and that will increase the code size by twice. And the code size being smaller is important in embedded, because the memory that holds those smaller code can be more energy efficient. Many times, the offset could be even a constant offset and need not be calculated. For example, in structures which are allocated to the memory, the offsets are typically constant and they are straight away added into the base and could in fact be folded into the instruction itself. Typically, in all embedded processors, there is a dedicated adder for address calculation. Typically, this address calculation is carried out in what is called as address generation unit, a specialized function unit dedicated for this job. And by putting these addresses which stream constantly through this address generation unit, exotic modes for addressing could be supported as post increment. What is post increment? Imagine one accessing a piece of memory over here at this location, and the next access that is desired is over here, which is by a fixed amount, let's say 4 locations. So we have a special addressing mode in some embedded processors, especially DSPs, which will straight away add 4 upon the first access's completion and make the next access go to this memory location, which is 4 units apart. This is called as post increment because once the load or store at this particular location is about to complete, that address which is participating in that load or store is taken, a constant fixed offset which is such as 4 is added to it, and the address now points over here. By post incrementing the address register, we are able to go straight away to the next location without having to load a new address into the address register, which would have costed us another instruction. So things such as post increments allow us to keep the code even more compact and of course give the freedom to the compiler to arrange these data in a nice layout which will take advantage of this mode. Later in the class, we are going to look at a specific optimization which is heavily used in DSP code generation called as post-increment layout optimization. The different types of operand widths that are supported in embedded world make a huge difference in terms of the internal organization of the buses and in supporting these addressing sizes. For example, take a look at this simple organization of data paths in an embedded processor. What we have is 2 different kinds of processing modes. One is for the regular 8-bit operands that are present, which are going through the set of buses over here. However, in addition to the regular 8-bit, we also have a operation supported for 12 bits. Why is that? Mainly because in certain processing modes, we want 12 bits processing. And what we could do is, in such cases, separate that into a yet another set of instruction, such as load irregular. What it will do is, it will go via this bus to the memory, pick up 12 bits and bring them in, and it will try to feed it directly to an instruction to use it. Or it might even be able to break it down and take only 5 bits out of those 12 bits and store it in the internal RAM, which can be used for processing later. So in this way, we can support subword level parallelism or irregular size of operands by using these buses, which are supported in some embedded processors. 5 bits, for example, are typically used in many controllers. 12 bits are typically augmented instructions in DSPs, which can add certain other modes to a regular size of operand. The last slide illustrated the importance of subword parallelism and irregular size of buses. In addition, in many modern architectures, we also have support for wider accesses, which we call as register pair accesses. Where do we encounter these things? Typically in high precision or extended floating point operations. An example of this is double, which is used in C. In case of such wide operands, it takes a coupled pair of registers to hold those 2 sides of the operands. For example, if you have a 64-bit operand and only 32-bit registers, and 64-bit operand is typically for high precision double operations, then we'll split that double into 2 parts, and a register pair will hold 2 pieces of this, each consisting of 32 bits. A register pair, remember, are 2 consecutive registers which are designated to operate like a pair. And so there are special instructions which will be able to deal with register pairs, add their values, do some other ALU operations on them, and so on. Many times, these register pairs are also used for even higher degree of subword level accesses. In such a case, one could get a register pair which could hold 64 bits. Each register could have subword level parallelism as 16 bits, and therefore we could have 4 such things executing concurrently. However, remember that register pair operations are typically slower, because remember we had to load 2 registers instead of 1, and it depends on the supported bandwidth whether we can do that concurrently or whether we have to do it one after the other. Typically, the solution for register pair access is as follows. We have a dedicated multiplex unit. In other words, first the lower register is loaded in the register pair, and immediately as this load is completing, the dedicated multiplexer switches the access to the higher register and starts loading that register from the memory. In this particular way, we can carry out certain overlapping of those 2 registers through these dedicated multiplex units. And therefore, the cost of loading 2 registers is lesser than the addition of the cost of loading 1 register at a time. In other words, if it costs us loading 5 cycles for a single register, it doesn't cost us 10 cycles for loading a register file, because we can partially overlap the first register and second register loads. Typically, it would cost us, let's say, 7 cycles due to such an overlap. So the register pair approach has many advantages, including simplifying latencies of loading wide operands by giving them lesser latency. And the second is in terms of increasing the subword level parallelism. Using the memory for loading double registers or a register pair can be tricky, because the data can be misaligned in the memory. And in general, for misaligned data, we need to worry about how to get it aligned first and then process it. So let's work through an example to see how this really works. So here is an example which shows how the misaligned data looks in memory. What we would like to do is operate on these 4 bytes of data which is sitting in between here and over here. However, as you can see, the memory is addressable only on 4 byte boundaries. In other words, one can only get a chunk of memory starting at this location and consisting of 4 bytes, and one can get the next byte starting at this location, and that is this particular part. So how can we get something which is in between from here to there? What we do in such cases is we go ahead and load the 2 parts of the memory in a register pair which looks like this. So let's say this is register R0, and let's say this is register R1, which is a register pair. We loaded the blue part in register R0 and we loaded the brown part in register R1. Having done that, we now do a shift on register R0 by 1 location or 1 byte, and we shift it in this particular way to create room for the data over here. In a similar way, we shift the register R1 down by 3 locations to create room for data over here. And then finally, in the CPU, we do an operation which will combine the register pair R0 and R1 into a single register. And if we do that, you can easily see that the lower part of this data which is sitting over here can get into this location, and the 3 parts of the data which sit in these locations get into those locations. So in this way, you can see that for any misaligned data, we can align it properly and get it right in the registers by taking help from a register pair, by first loading it as it is and then shifting it as appropriate and then merging together to create the properly aligned data. And this is one of the biggest uses of register pair. Now you may ask me, why this misaligned data in the first place? Well, many times in order to pack the data, one has to live with misalignment. If we had odd sizes of data which do not fit into the 4, then some of them could spill over and go into the next location, which is what has happened here. You can see that some other data ended here, and we had to pack this data, and it ended up overflowing into the next location here. So in order to save on the size of the memory, we pack it, and that could create misalignment. And this is one of the biggest uses of the register pairs to correct the misalignment before it is processed in the CPU. Having seen how to correct the alignment, now let's take a look at what if we try to access some data which is misaligned. So let's say there is some address and you put it out on the address bus and you try to access the memory which is misaligned, then what happens? The architecture typically causes an exception if you try to access data which is misaligned. And so typically the architecture raises an exception through an exception handler which tries to say that you try to access some data which is not on the word boundaries. However, such exception handlers are very complicated, especially in wide issue machines, especially the ones which involve VLIWs. What is the complication there? The complication there is maybe how about some words are accessed in aligned manner and some other words are accessed in non-aligned manner, then what to do there? So in VLIW, the solution that is implemented simply treats misaligned accesses as non-recoverable exceptions. In other words, it tries to just discard the complete set of instruction which is trying to do that access. So if there are 4 such sub-instructions, some of them are aligned, some of them are misaligned in terms of their accesses. The whole VLIW instruction will be treated as non-recoverable and the exception handler will try to take some action on the instruction as a whole. Finally, let's take a look at caches and local memories, which are important parts of the microarchitecture. So one of the important things we are going to look at is something called as prefetching. What is prefetching? A prefetching is a hint that a particular location is going to be used very soon and you must get the data ahead of time to avoid the latency penalty. So one of the goals of prefetching is to get the data from memory into caches early on with a view that that will get used very soon. And so when the actual load hits, you have a hit in the cache and the data latency is reduced. Here's a simple example here that in anticipation, the dog is trying to take a jump here to get to the data. So prefetching means anticipating things. Of course, in a real-world sport, taking a guess early in anticipation of the ball and positioning oneself is very useful. But as far as our processor is concerned, taking those guesses can have a second side. What if the guess is wrong? Well, in a sport, a wrong guess means a lost opportunity, but that's not just the case in prefetching. Again, remember what is going on in terms of prefetching. The data is brought from the main memory into the cache ahead of time in anticipation that the next load will actually get the data from the cache. Now, take this particular situation. You brought the data, but somehow the next load did not access that data. There could be multiple reasons behind it. Maybe the load just didn't execute, or maybe the load has a different address attached to it. Under both of these circumstances, the prefetched data just sits in the cache. What it results in the bandwidth wastage. And in fact, a precious resource like cache now is occupied by useless data. This particular aspect is called as pollution. What is polluted here? The cache is polluted. How it is polluted? It is polluted with a data which never gets used. And so some other useful data is dislodged and you in fact take a performance hit in this particular case. So as we saw, prefetching has 2 sides. The useful side is data is readily available in the cache and so the latency penalty is avoided. The other side is a wrong piece of data is brought in and it displaces the right piece of data which is in fact needed, which is caused as cache pollution. So how are these things solved? One of the solutions is replacement policy hints. In other words, when you prefetch a given piece of data, which data should be dislodged? That is specified by this replacement policy. In many cases, the replacement policy could be as simple as do not displace a neighboring data because there is a locality associated with it, which is special locality. The second kind of hint could be temporal locality. Do not displace the data which has been most recently accessed because there is going to be another access to those data pieces in near future. So if one specifies whether the current locality is spatial or temporal, then one would avoid dislodging the wrong piece of data. In spatial locality, we will not dislodge the data which is sitting in the neighborhood of the data that is brought in terms of the cache lines and address spaces, whereas in temporal locality, we will not dislodge the data which is most recently used. Sometimes the issues of locality are purposefully decoupled from the issues of prefetching. For example, there is a special type of cache called stream buffer, and it acts like a data cache for special locality. In other words, the data items are streaming as streams of addresses which are next to each other, and they are implemented through a simple buffer which is first in, first out. Such a buffer is called as stream buffer. Here is an example of a stream buffer which is acting in what is called as a FIFO manner. The data which enters over here continues to get pushed on the right hand side, and a data which enters later gets filled in from this side. So this buffer is getting filled in from this side, and eventually the data which enters here is brought here and is then accessed through the load which takes it out of the other end of the buffer. Once that happens, the data is gone. The data which came right behind it is now becomes available for the next load. So in this particular way, the spatial locality is implemented by keeping track of the data items which lie next to each other and letting them stream through this FIFO buffer. Now turning to the other important aspect of caches, let us focus on the latency itself, which is one of the most important reasons for caches. Embedded world is one of using deterministic processing or repeatable execution. What is a repeatable timing behavior? A repeatable timing behavior involves execution of the same program multiple times. Each time you execute it, it should produce the exact same amount of time. Why is it so? Because a lot of embedded software is very interactive, and different times when you execute, if it produces different time, the users will think the programs are hanging and they will not even work properly in a distributed environment. So not only the latency should be small, but it should not be variable. That's a key goal of embedded world. So most caches have variable latency. If the data is found in the cache, you get one type of a latency behavior. If it is found in the next level of cache, you get another type of latency behavior. If it is not found and you go all the way to main memory, you get another kind of latency behavior. In embedded world, because the timing of the program will keep varying each time it executes, this is unacceptable. And so variable latency is an absolute no-no in embedded world, and therefore the memories are designed to behave like caches in terms of the fast access to the data, but are really not variable latency. So there are local memories here which just hold the data and which do not evict the data, but let the software control the placement of the data and eviction of the data. So in that sense, they have the speed of the caches, but they do not have the variable latency of the caches. In some other cases, we have lockable caches. What are those? The lockable caches are the ones in which the data resides in the cache and is not evicted because the cache line is locked. And therefore, we are able to get the data from the cache with a guarantee and not with a variable latency. So in other words, the memory in embedded systems is organized in a different way and is organized so that the latency behavior is repeatable. That results in deterministic memory latencies and allows us to write many real-time software. Again, as I mentioned, the memory is typically organized as a scratch pad. It does not have any inclusion properties. In other words, the data need not be present in the higher memory hierarchies. It could be purely locally kept into the local memory, and once it is done, it could be simply abolished without ever writing it back into the main memory. As we mentioned, which resides in the scratchpad memory at what time, which data resides in that memory at what time, is completely under software control and therefore is deterministic. Typically, the compiler controls the scratchpad memory in terms of the data placement. In some cases, the memory is also content addressable or is associative. For example, if you give a packet ID and want to find out the header part of the packet, it is content addressable. You do not generate the address, but just index it based on the packet ID. And that really allows you to keep the memory access very efficient without creating multiple accesses. Now, what is wrong with multiple accesses? Again, the property of determinism. If you know that a given operation at a higher level is going to result in a fixed number of accesses, such as those in the content addressable memory, then the timing behavior of the software is deterministic and is not going to change based on the number of accesses. And that is why content addressable memories are very important in embedded world. Now let us test our knowledge of caches, especially in terms of the locking mechanisms. How do they work? Through a simple quiz. What we have is a wave locking memory and a line locking memory, and you're supposed to identify which is a characteristic of which. So let's read those characteristics over here. Option A is a coarse-grained approach to cache locking, where locking is available at the granularity of ways of a set associative cache. The alternative B is, it is a more fine-grained approach to cache locking. In this interface, the locking mechanism is available at the granularity of a single cache line as opposed to a single way. Please go ahead and match these definitions to different mechanisms for locking. So please go ahead and write your answers now. Let us consider way locking. Way locking is corresponding to alternative A. And what is it? It is a set associative way of locking. In other words, whatever is in a particular set is what is locked. As against this, alternative B is appropriate for line locking. You can easily see that the line locking is at a much finer granularity and allows you to control the lines which are exhibiting spatial locality to be locked together rather than just the way in which they are mapping inside a cache. Line locking is much more used in practice than way locking because it is able to implement the spatial locality. Finally, the description of microarchitectures will not be complete without talking about some of the exotic addressing modes. Why such modes? Because remember, some of the embedded chips are really domain specific, such as DSPs, and getting the processing done at the real-time speeds is of ultra premium. The only way to do this is to get around the memory latencies in terms of implementing those operations as fast as possible, and nothing more than the addressing modes serve that particular purpose. So let us take a look at what are the different exotic modes that are used in some embedded systems and why, and what do they mean. Sometimes we have a need for accessing uncached data, or sometimes we have a need for getting the data on the on-chip memory in the absence of the caches. All these requirements are typically served pretty straightforward way by using the regular load stores. They don't need any speculation because there are special instructions which will load the data ahead of time onto the on-chip cache. And in case of an uncached access where there are caches present, a regular load will eventually go to the memory hierarchy. In order for a regular load to be forced to go to a non-cached version, sometimes there is a special addressing mode such as load from a specific memory hierarchy, and that has a fixed cost associated with it in terms of the latency. For example, ld.m would tell that this load is always to be fetched from the main memory as against from a cache. So you would be given two options, ld.m and ld.c. The ld.c would try to always fetch the data from the cache, and ld.m would always try to go to the main memory and get the uncached data. You will have exact control over latency and residency of the data through the use of these two instructions. Let's now take a look at what to do to facilitate higher data bandwidths. Remember that when we process an instruction, the bigger challenge is not to get an instruction but to get the data. And in order to facilitate higher bandwidth for the data moment, hardware architecture typically uses the instruction bus as an additional data bus. In other words, the two operands, one of them is brought by the regular data bus and the second one is brought by the instruction bus. In this way again, we can cut down on the latency of the load. Let's look at the third one here. We already talked about it in the banked memory discussion. A specific organization of banked memory is called as XY memory. What is XY memory? It is to stream two large arrays so that we can cut down on their latency. Where is this situation encountered? Typically in convolution codes. What is a convolution code? It is to take A of I and do a convolution operation with, let's say, B of I. A of I is a vector which is containing one type of a signal, B of I is another signal, and we want to do the convolution, especially in DSPs, to do certain signal processing. Now, A of I would be held in the X memory, B of I would be held into the Y memory, and these are the two different memory banks which can be parallelly accessed, and therefore we can do this convolution operation over here very fast. Let's go to yet another mode which is called as circular addressing mode. Again, we had talked about it earlier. Where did we talk about it? We talked about it in software pipelining. What is going on there? We are accessing the addresses on a very large address space in a particular pattern. For example, take this AI is equal to AI plus 1 as a code. You can easily see that in the memory, it will look like this. Here will be AI and there will be AI plus 1 right next to it. And as we perform this operation, all we would be doing is carrying out a shift from this memory into the previous memory. And through circular addressing modes, this will be facilitated very heavily by carrying out such shift into memory locations that are neighboring to each other. And so the code that could be generated by the compiler for AI is equal to AI plus 1 can make use of such addressing mode, and the store and the load could be changed by using such an addressing mode into a single instruction and can cause extremely high efficiency shifts. Now this operation is quite common, especially in signal processing, because again, you want to get rid of certain parts of the vector, you want to mask certain values, you want to move them into different spatial locations and so on. So this is one of the important modes which allows you to do that. The second case we have covered important topics in this lesson: clusters, registers, addressing modes, and alignments. You should now be able to clearly appreciate the register and memory organizational differences between traditional computer architectures and the embedded system architectures.